Hello, I am Professor S. Shankaran in the Department of Metallurgical and Materials Engineering.
What is torsion test? So torsion test is done on a solid bar, which is shown like this. And what is involved in this test? Basically, application of twisting moment, MT. Okay, causes an angular displacement, that is rotation of the bar about its axis. Okay, so the twisting moment will have the units of Newton meter, like force into distance, right? That kind of unit it will have, which causes angular movement or angular displacement, I would say, rotation of the bar about its axis. You can see that this is the angular uh, displacement. The external movement is balanced by the internal shear stress developed in the, internal shear stress developed in response to the external movement. So basically, the shear stress which is developed in the body resists the external movement. That is the idea. So these two forces are balancing with each other. So now we look at this diagram little closely. So a twisting moment MT is applied, and this results in relative angular displacement of points along the circumference of the body. So this angular displacement occurs in the circumference of the bar. So this is what it is. And the relative displacement varies linearly with the axial separation distance. So this is the axial separation distance. So we are talking about the relative displacement which is varying linearly with the distance L. So the external moment gives rise to internal shear stress that resists it. The shear strain varies linearly with the radial position within the bar, increasing from 0 at the bar center to the maximum on the circumference. So it is from R is 0 here, and then it goes to maximum on the circumference. So that is basically a shear strain. So what is this? Before even getting into the detail, the torsion test is something the way in which we have to look at it is you look at the um, mechanical behavior which involves a large shear strain. Okay, one of the large shear strain which is involved, and how the material behave. So far we have looked at most of them are, there is a plastic strain, shear strain, everything was there, but nothing compared to this kind of a large strain. So we are looking at a material behavior, mechanical behavior involving large strain. That is something you have to remember. So the shear strain gamma is given by, so you can simply look at this geometry. This curve length is r theta. So r theta by L is tan phi. So this is tan phi. So normally this theta by L is denoted by theta prime, that is theta prime, where r represents the radial position, theta displacement angle, and L the axial separation distance. The parameter theta by L is frequently expressed as theta prime, the angle of the twist per unit length. Okay. So now look at the mechanics as usual, very important and interesting. The stress state developed in torsion is a biaxial one, very important, with the principal stresses related by sigma 1 is equal to minus sigma 3, with sigma 2 is equal to 0. So you see this sigma 3 and then sigma 1 and then shear stress wherever it is acting. So this schematic clearly shows the state of stress. With respect to the system of axis of the figure, the maximum shear stresses are developed in the y-x plane. So Y explain the maximum shear stresses produced. We can now fix them in a Mohr circle to understand more clearly. The Mohr circle representation of the torsional stress strain. Larger shear stress is relative to the normal stress. That is, tau max is equal to sigma 1 minus sigma 3 by 2 is equal to sigma 1. Okay, normal. So the relative to normal shear stress are found. That means large shear stress are found in the torsion, and the test therefore is useful for facilitating plastic flow. So you can see that sigma 1 and the sigma 1 is equal to minus sigma 3. So sigma 1 is this, and then this is minus sigma 3, and sigma 2 is 0. So it is in the center. The maximum is here. So which is tau max equal to sigma 1 minus sigma 3 by 2. So this is nice. So for the elastic deformation, the shear stress also varies linearly with radius. By balancing the external twist moment with that arising from the internal shear stress, we find that the latter is given by this formula. This is simple mechanics. So tau is equal to 32 mt times r divided by pi d square. So during the test, okay, first we will see this. During plastic deformation, shear strain still varies linearly with radius. However, the shear stress does not. Okay. Thus, this equation does not hold for plastic shear strains. Okay. However, methods have been developed for calculation of tau sigma curve from the mt versus theta. So in a typical torsion test, what we measure is mt and theta. From there are methods which are developed in the standards to how to conduct this test, which will finally evaluate a tau shear stress versus shear strain plot. So that's the idea. The stress state characteristic of torsion leads to development of large maximum shearing stresses relative to the principal normal stresses. Okay. The tendency of plastic flow relative to the fracture, the ratio of tau max to the mean pressure, that is sigma 1 plus sigma 2 plus sigma 3 by 3. This ratio is infinite for torsion testing. Very interesting observation here. Okay. So it clearly shows that the large plastic flow or shear flow is involved in this test. So that's some basic mechanics about the test and the test details. By contrast, it is only 1.5 and 0.75 for a simple, that is sigma 1 is greater than 0, sigma 2, sigma 3 is equal to 0. And biaxial tension, sigma 1 is equal to sigma 2, which is greater than 0, and sigma 3 is 0, respectively. Okay. So this is for 1.5 for the simple tension and 0.75 for the biaxial tension. This characteristic of a torsion test makes its employment worthwhile in many situations despite the difficulty in its execution. To look at the real characteristic of how the material behaves under the large shear deformation, it gives much more useful information. Now move on to compression testing. This is also quite popular and important these days, especially researchers who do not have sufficient material to produce bulk samples. Normally they produce a synthesis material in the laboratory and then make powders and they compact them. They produce small cylinders and then try to estimate the mechanical behavior. So compression testing is quite popular in nanomaterials research because of the lack of availability, lack of material availability, right? So what is involved in compression testing? So the cylindrical sample, which is the diameter is about A and height is H, is being compressed by between the two plate ends. And what is the special design is given here? Suppose if the cylinder what we have prepared after the compaction, if it is not uniform and symmetrical, that means the H1 is smaller than H2, then this delta H has to be corrected. Otherwise, the load distribution will not be uniform, okay, which may lead to a problem. So that is this is called length inhomogeneity, right? So the inhomogeneous loading is eliminated by hemispherical cap. So now we understand. So this hemispherical cap will takes care of this kind of inhomogeneity, okay, which can rotate to accommodate the difference in the height. So this hemisphere geometry will takes care of this inhomogeneity. However, if the surfaces of the specimens are not flat, stress inhomogeneities will arise, which can cause significant differences in the stress strain response. So we have to be very careful about the flatness of the specimen surface before we engage them into compression testing. It is not a good practice to have the stresses on the two sides vary significantly, as this will result in erroneous strength determination. So especially the strength between the two sides, the stresses between the two sides basically should not vary significantly. The use of Teflon or a thin metallic shims also helps to alleviate the problem. Okay. So what is mechanics or plastic deformation information? So this is a typical stress strain curve for a compression testing. So in this case, it is 70-30 brass, and we will see the details. The figure shows the typical compressive stress strain curve for a metal 70-30 brass. The engineering strain curve E is concave, whereas it is convex in a tensile test. So that's a simple and first observation. It is a concave. Okay. In contrast, the true stress and true strain curves in tension are displaced to the left on the strain axis and up on the stress axis from the engineering stress strain curves. So you can see that when you take the true stress true strain curve from the engineering stress strain curve, it looks very different here. See, what you need to understand from this flow curves, the basic mechanics involves the yield criteria. Everything is same, whether you pull it in a tension or a compression, okay, or pull it in biaxial, triaxial, and so on. So instead of the material response in terms of stress and strain data, generally you can call it as the flow curve, flow response, flow properties. That's why in some of the slides we have seen that we have effect of strain rate on temperature on flow properties, right? So we can see that it's a flow curve again in a compression load. The phenomenon of necking is absent in compression loading, and much higher strains are reached. Okay, there is no necking in this test. However, necking is replaced by barreling, a non-uniform plastic deformation resulting from friction between the specimen and the plate end. So what is this? this region is marked as barreling. So, which is very, very important. How does it appear? So, suppose this is the initial sample with the A equal to 5.05 millimeter, sorry, and height is 6.70 millimeter. So after it subjected to compression, so you can see that both sides are bulging. So that is called barreling. So that takes quite a bit of non-uniform plastic deformation. Okay, that is because of the friction between specimen and the platen here. This barreling is responsible for some concavity in the true stress strain curve at a strain greater than at least 0.4. So you can see that this region we are talking about, and limits the range of strain in compression testing of ductile material to approximately minus 0.3 to minus 0.4. It will be shown through a stress analysis that frictional effects play an increasing role as the length to diameter ratio is decreased. So this is one big challenge. What kind of length to diameter one should choose for getting a reasonable good data which describe the deformation characteristics in the compression mode. Okay, we will see what are all the challenges. So what you are seeing here is this is x-axis is a distance and y-axis is pressure. The pressure or a compressive stress is not uniform over the top and bottom surface of the specimen. This is a first limitation we have to understand. Okay, it is not like the material is subjected to almost uniform strain in the gauge length in the tensile specimen, but in compression the pressure or the compressive stress is not uniform over the top and bottom surfaces. So the variation of the pressure on surface of the cylindrical specimen being shown here. Okay, so this is a pressure. So this is A, and so positive axis and negative axis. The pressure differences can be calculated from an equation derived by Meyers and Chawla, which is given in this form: P is equal to sigma naught times e to the power minus mu times A minus R by H. And this is the equation for the friction hill. So what is friction hill? So this is the hill we are talking about, friction hill. The pressure increases and reaches a maximum at P max in the center of the specimen, the top surface of the specimen. So it comes basically because of the friction between the platen and the specimen surface. So that is why it is called friction hill. So the pressure reaches a maximum in the center. The compressive stress at the outside, that means when R is equal to A, we are talking about this center, and if this becomes equal to A, then if you put R is equal to A, then this equation becomes P is equal to sigma naught, right? So that means up to this point. So there is no friction hill effect. Okay, but then as long as the compressive stresses are measured in this kind of a dimension, we are going to have this friction hill effect, because it has got a different effect of A by H ratios. The greater the ratio of A by H, the more the severe the problem is. This is what I just said. The frictional problem will be more for the higher A by H ratio. The pressure arises exponentially toward the center of the cylinder. The greater the coefficient of friction, the greater is the Pmax. So the idea is you can reduce the friction to reduce this effect and make sure that the proper A by H is chosen, and the geometry of the specimen is also taken care, make it uniform, flat, and so on, to get the reasonably good data. A friction coefficient mu is equal to 0.15 is a reasonable assumption. It is instructive to calculate the maximum pressure for 3 A by H ratios. So it is recommended to have, at least by these authors, Meyers and Krishan Chawla, they recommend that you measure these A by H for 3, which is A by H2, A by H1, and A by H5. So measure the P max. Okay. So this is the kind of some details about the compression testing, which is quite different from the tensile testing. So I thought you should know. So now we will move on to brittle solids. So we looked at metals, we looked at polymers, and we also looked at compression testing for small specimens. And we will now look at the brittle solids. How do we measure tensile strength of a brittle solid? Because fabrication of the sample itself is going to be a limitation. We cannot fabricate them, we cannot machine them. So the room temperature behavior is usually elastic with a brittle failure. So we have a method called 3-point bending test, which is often used. Okay. So 3-point bending test is done with this kind of a geometry. It can be, the specimen can be of cross-sectional, I mean the specimen can have a cross-section dimension like this, or it could be a circular cross-section. And this is the geometry where force is applied here, and which is supported by these two, fulcrum kind of setup here. And this is a midpoint, D midpoint deflection is shown here, from here to here, how deflection is measured. So this kind of geometry and relations are given by the strength of materials concepts, and we are just going to look at the equation straight away. We are not interested in looking at this derivation because they are all available in standard handbooks. So here what we are seeing is force versus displacement data, and slope is F by delta, and the Young's modulus is given by F by delta because it is elastic still, so which is equivalent to L cube by 4 BD cube for the rectangular cross section, and the same can be given for the circular cross section, which is L cube by 12 pi r to the power 4. So these two relations will take care of the elastic modulus measurements for the brittle solids. Okay, this is also quite a common test people use. For the measuring the same type, again 3-point bend test. The formula is different here. It is called flexural strength. Okay, this is not called the yield strength or tensile strength. Here it is called the flexural strength, that is sigma Fs, is given by 1.5 times F means flexural force, which is a flexural test, times L divided by B d square for a rectangular cross section, and FL by pi r cube on the circular cross section. And we quickly look at glass properties, because if you look at, if you are thinking about a deformation of amorphous material, then glass is very important to know. So what is that we need to know about before even look at the mechanical behavior? So this popular curve everybody should know first, right? That the specific volume versus temperature. And the liquid is cooled and then it goes through, this is a crystalline form and this is a amorphous solid and this is a super cooled liquid. Okay, so the specific volume versus temperature plot. And for crystalline materials, you all know that it crystallizes at melting point and have an abrupt change in the specific volume at melting point. These are all we know that. For the glasses, they do not crystallize. The change in slope in the specific volume curve at glass tension temperature is Tg, and they are transparent and no crystals to scatter light. They are all basic characteristics. And again, what we need to know is what factors affect the melting point and Tg. Both Tm and Tg increase with increasing chain stiffness. In the case of when we talk about chain, again we are talking about silicate molecular chain and all that, right? And chain stiffness increased by bulk side groups, or it could be related to some semi-crystalline polymer materials as well. So that's why all this the molecular arrangements are coming here. Polar groups or side groups, double bonded and aromatic chain group, they are all going to increase the chain stiffness, and which in turn have influence on Tm and Tg. So that's why brought here. So, but our interest is deformation. So, whenever we are going to discuss about deformation about the semi-crystalline or non-crystalline materials, we should recall our initial, lectures where we talked about time-dependent deformation. Okay. How does that related here? So this is a Young's modulus versus E versus T plot, where you see that ER is the reduced elastic modulus, and why we are talking about it, we will come back to in a minute. So there is something called stress relaxation. We have already seen this term, so I can go pretty fast. We know what is stress relaxation. Relaxation time and all we have seen. What is relaxation time and all? So strain to epsilon naught and hold. So strain the material to a specific strain or fixed strain and hold it and observe the decrease in the stress with time. So that is stress relaxation tests typically. It is done normally in the amorphous materials, and then we try to calculate something called relaxation modulus, that is ER, as a function of time, which is equal to sigma T divided by epsilon naught. So that's what typically calculated in a stress relaxation test, and then E versus T is measured here. So that will show some kind of where all the polymeric materials will stand. So for the rigid solid, a small relaxation, and this is a transition region. So this is a viscous liquid, large relaxation. Okay, so the Tg is somewhere here. So we can now relate to the mechanical deformation behavior. Where does this our material lie in this map? So depending upon that, it will you will see the mechanical response. So some of the typical polymer materials are given and their Tg values, and then we will be able to we can relate that to mechanical behavior. So the same plot is given in a different form. Sorry, and you can see that this region is a glassy plateau, and this is a glass transition region, and this is a rubbery plateau, and then this is a viscous flow. So you can see that the different regions of this curve characterizes the different, I would say the classes and how the material behavior is going to change as a function of uh, homologous temperature. Again, this is it is not homologous here. It is temperature normalized by Tg, not melting point. Okay, if it is normalized by melting point, it is called homologous temperature. So, having discussed about the different temperature effect, the viscosity in non-crystalline materials becomes important because that only related, which only can be related to the shear stress and the velocity gradient. So whenever we talk about deformation, this is the one primary equation you have to keep in mind. Tau is equal to eta times the dV by dy. So it's a velocity gradient. Suppose glass can be subjected to shear stress, and then this is the formula. So how viscosity decreases with the temperature? These are all shown from these plots, because the viscosity, as long as the material is not in the viscous form, you cannot just work the material or even deform them. So some of the examples of different type of silicates and glass and soda lime are given, and then it is just given the red region where the temperature under which the material exhibit a softness or soft, at least soft enough to deform or work. You can, a glass forming a plant will have the typical viscosity of the glass melt, and then they blow it, right? The glass blow it and all that. So it's quite important and kind of application. So let us now look at the plastic flow of non-crystalline solids in a much more fundamental way. What I have shown is like an application point of view, but let us look at science behind it. What is involved? So it is a non-crystalline solid. So you can see this atomic configuration is not done by any order. The atomic configuration will be completely disordered. Okay. So we are going to look at the effect of shear stress. Suppose if you apply the shear stress to this kind of a cluster of atoms, and then what happens? So what is that we are basically seeing? So suppose if you follow this A, B, C, D atoms in a disordered range, and then when we try to apply the shear stress, what happens? So these atoms are now trying to redistribute in the nearby region. So what is the driving force? The driving force is the free volume which is available next to this cluster. So that is the A atom. You can see that it is coming, it coming to this, and then it creates another configuration. Then again it forms another free volume here and there. So that is how the deformation takes place. So the amorphous material responds to the shear stress in this manner with respect to the free volume available. So this is called a viscous flow in an amorphous material, and this is a response to applied shear stress, which induces a flow of upper portion of the material with respect to the lower. The flow is accompanied by the atomic or molecular jumps. As shown here, the most such displacements occur in regions where the local atomic volume is highest. So wherever the local atomic volume is highest, this kind of rearrangement is going to happen, or a displacement is going to happen. That is how the deformation is being accommodated. So what is the driving force? The energy reaction coordinate diagram is for the process is given here. Whatever the process we are talking about, this is the energy reaction coordinate. So what you are seeing is the atomic displacements require an activation energy, that is delta U. But the displacements are stress aided with an energy tau V act. V act as an activation volume. So though the atomic displacements requires an activation energy delta U, the displacements are stress aided with an energy again, it is also aided with this shear stress times the activation volume. What is activation volume? We will see this aspect in the next lecture, especially. Basically, the volume under which the complete disorder can be taken. Okay, wherever the most disordered regions are there, the volume where the in a typical way in a crystalline material, we can talk about the most dislocated volume. Okay, the dislocated volume we can say about. So here it's about highly disordered volume, because in amorphous material we don't talk about dislocations, right? So that's why we are talking about a free volume. So wherever the disorder is maximum, okay. So here that is activation volume, which the same terminology we use in crystalline material also, but where we relate that with the dislocation density and configuration and so on. We will see it in the next lecture when we talk about it. Basically, kinetic principle determines the stress-strain rate relationship. Okay, so how do we understand this? Yeah, if you look at this diagram, this is quite interesting, and though it is quite, lot of information is there, but if you slowly understand what is plotted here, this is shear stress normalized with the shear modulus tau by mu versus temperature. Since we just discussed about the deformation of non-crystalline material completely depend on the temperature. As only as a function of temperature we can talk about it, because these materials have to undergo a different transformation to basically elastic to viscoelastic and then plastic and so on. So if you look at this different boundaries marked in this region, it is quite interesting. So at the low temperature, the non-crystalline solids exhibiting a homogeneous flow. So this is a temperature range, and then it will be a linear elastic behavior in this range. Okay, and then little below the Tg, then it is viscoelastic behavior. Okay, so it is viscoelastic behavior, and then just a little above the higher stresses, it is solid, and above this, it is at high stresses, it is inhomogeneous flow. So how do we understand inhomogeneous flow in a non-crystalline material? So this is typically, this plot is drawn for a typical metallic glass. Metallic glass is a non-crystalline amorphous metal. Okay, so we will just try to see what is each boundary will describe. So it is called deformation mechanism maps for metallic glasses, which include the linear elastic, viscoelastic regions, and they are not shown in the low temperatures. Suppose if you plot this same graph in low temperatures, these are all not there. That's what is shown here, which are not discussed in the very low temperatures. At high temperatures, from the melting temperature downward to about Tg, so this region, we are talking about this region, the glass deforms in a Newtonian viscous manner. So just below the Tg, about this stress range, the material will obey the Newtonian viscous flow. Just 2 slides before, we have seen that how the shear stress is equal to eta times dV by dy, right? That strain gradient, shear gradient, we have seen that, right? So that is the Newtonian flow. Further, the permanent deformation is distributed uniformly throughout the material volume. Okay, so this is about how it will deform after that. At lower temperature, that is less than the Tg, and lower stresses, this corner, the flow, whether elastic or permanent, is also homogeneous. So it could be elastic or a permanent, but it is homogeneous flow here. Okay. However, at high stresses, at low temperatures, so high stresses here at low temperature. So this is a region. Permanent deformation is heterogeneous and takes place by formation of shear bands. Very important point. So metallic glasses are non-crystalline solids. At high stresses and low temperatures, they deform, or the permanent deformation is heterogeneous, and they are characterized by the shear bands. Very important point. Okay. So we were talking about in crystalline materials, slip and shear bands and all that. There also we talked about shear bands, deformation bands, and so on. Here there is nothing like that. Here we are only talking about a shear band formation, right? Further, the strain rate sensitivity of the flow stress is reduced at low temperatures. Obviously, this we have already seen at the high temperature deformation when M is the, where we characterize the M at high temperature, it is almost equal to 1. We have seen that, right? There also we talked about the Newtonian flow. When M is equal to 1, it becomes Newtonian flow. But at the low temperature, it will obviously get reduced. Okay. So we will stop the discussion on the tensile behavior with this, because I thought I will just bring in a little more material other than metals, right, to get the basic ideas about how the deformation takes place in other class of materials. Okay. So we'll stop here, and then we will continue in the next lecture. Thank you.